pleasure to introduce here the talk of Anders Zolgaard from Copenhagen. He's here at the opportunity of the tomorrow's defense of David Mariček. He's his opponent, and the floor is yours.
Great, thanks a lot. And thanks for inviting me to this awesome department. It's by far the most beautiful department I've ever seen, with the best office window views that I've ever seen. Still kind of mind blown by that. All right, today I'm going to talk about, so learning under bias and NLP is the title, but I'm going to talk about two very sort of practical, related but different problems. And to sort of get the problems, I want you to just for a moment sit back and relax and sort of picture the following two scenarios. So one is you're in this project. You're with a bunch of bioinformatics people, and you're the NLP guy. So you're the processing guy and you're the parsing guy. And these guys want to do data mining, relation extraction, whatever, and you're supposed to parse all these biomedical research articles. Now, they're in English, so all you have for training your model is Wall Street Journal. And you're a little worried about that because you might think that, the biomedical language is going to be a little different from the Wall Street Journal. So your data is going to be biased somehow. Now, that's the typical domain adaptation scenario. We all know that. Sometimes we just don't know what to do about it. Okay. The other scenario that I'm going to be interested in is it's raising the bar a bit. It's a slightly more complicated scenario where you want to do NLP tools, or you want to do an online service, and something that people are going to use. So you're training a parser or a part-of-speech tagger, again in the Wall Street Journal, but you don't really know what kind of data your tools are going to be used for. So, people might want to parse Facebook updates, they might want to parse biomedical literature, they might want to parse emails, but you don't know. So the question here is, can we do better than just training our supervised parsers in those two scenarios? So in the domain adaptation scenario, of course, we're going to be interested in trying to adapt to the distribution that we're interested in this specific application. So for example, biomedical literature. In the other more complicated scenario, the question is kind of more open because we don't know what distribution we're trying to adapt to. Okay. Now that kind of sounds like robust learning, which, is something that people have been talking about for a long time. I'm going to try to go a bit beyond that, because even if we don't know the distribution, we might know something about what distribution differences are in general, and we can sort of try to minimize expected error on basically all distributions that we can think of. And that's what I'm going to be talking about. Now the talk is going to be, so I do tagging and parsing. The first slide is going to have a dependency tree in it. Then it's going to be machine learning, machine learning, machine learning, machine learning. And then at the end I'm going to get back to parsing and tagging. But for a while I'm going to be talking about classification only. Okay. I'm going to start off with just a very fast crash course in supervised learning. It's probably maybe too fast for some of you and just redundant for others. There's always this trade-off, but I'm just going to talk about a couple of very, very simple methods that I'm going to be building on. It's going to be like the cornerstone methods, like nearest neighbor, an A-phase, Perceptron. You probably know them already, but I just want to provide some common ground. Then I'm going to talk a bit about semi-supervised learning. Now, semi-supervised learning methods are established in the NLP community. A lot of people use them. And it turns out they can correct some of the bias in our data in the two scenarios that I'm interested in. It's just that they can only correct bias in some cases when the expected error on the target distribution is relatively low. And they can only correct some of the bias. Okay. Second, I'm going to talk about transfer learning. That's also a strand of research in machine learning, but less widely adopted in the NLP community. And then finally, I'm going to talk about this scenario where you don't know the target distribution in advance, but going a bit beyond just robust learning. And then finally, at the end of the talk, I'm going to try to put everything into the context of dependency parsing and part-of-speech tagging. Okay. And interrupt me if you have questions along the way. All right, so the primary motivation for all of this is going to be just these two simple observations, namely that we typically have relatively little labeled data in supervised NLP. Relatively little in the sense that we typically have more dimensions than we have data points, at least in a lot of cases. And we have, so for any test scenario that we can think of, even if it's in domain, we typically have a lot of words that we haven't seen before, a lot of diagrams that we haven't seen before, and so on. But moreover, the data that we have is typically also biased with respect to the applications that we're interested in. And that hurts performance in ways that are actually quite prohibitive for a lot of the technology that we're interested in. So this is the Stanford parser trying to parse I like do not swim. The Stanford parser is trained on data where you probably don't see a lot of adverbial or parenthetical uses of the word like, so it messes up on this one because it thinks that like is supposed to be the root of the sentence, which of course it isn't. This is just, you see these tables all over the literature. This is the Harbin Institute of Technology parser. It's a really good parser, dependency parser. Just results in dependency parsing and part-of-speech tagging. On the Wall Street Journal, it gets a labeled attachment score of 92%. Part-of-speech tagging accuracy is about 98, but that's on the universal tag set of Google, so just 12 categories. I'm going to flip a bit back and forth between the treebank tag set and the Google tag set today, so ask questions if you're going, 98, that can't be. I thought the world record was whatever. The interesting thing here is, of course, that the performance drops considerably when we go out of domain. So if you want to parse Yahoo Answers, BBC News Groups, Amazon Reviews, you see this performance drop of, in some cases, more than 10% in label attachment score. Interestingly, you see almost the same kind of degradation with part-of-speech tagging. So even part-of-speech tagging is a difficult problem when we talk about, processing things that are not Wall Street Journal. Okay. And so the objective today is to talk about methods that are going to improve not on these numbers, because I don't care about Wall Street Journal, but on these numbers. All right. Okay, back to computational linguistics 101. So this is probably familiar to you guys, but I just want to reemphasize how this works. So in general in NLP, we want to translate language into typically binary vectors. A really, really simple example that I'm going to be talking a bit about is the bag of words model text classification, where you represent something like this tweet. It's a tweet made under the 2008 debates. McCain just gave a cheap plug to Ed Kennedy. As for example, this vector here, what it says is just that of those 5 names here, all you see in this text is McCain and Ed Kennedy. This is a really simple bag of words model. Typically, you'd have a much larger dictionary or vocabulary, but that's essentially how it works out. So we represent the data points that we're interested in NLP as either binary vectors or real valued vectors. In fact, in the running examples that I'm going to be talking about here, I'm going to be using a TF-IDF model, so they're going to be continuous valued variables. Right. Then, in supervised NLP, we add labels to these data points, and that's what requires human effort. So, for example, we want to build a spam filter, we construct these binary vectors for all the emails, and we have some person sitting there saying, gee, that's spam, that's not spam, and so on. And we get this more complex tuple here with a class label and the data point. Typically, we're going to write boldface X for this part and Y for the class label. We're just going to assume that we're working with binary classification problems, and the values here are going to be either, the observed variables are going to take either binary values or real valued. Yeah. Oh yeah, right. It's just saying that thing 1 here at this list has the value 1 and thing number 4. So this is Python indexation, so to speak. Yeah, right. Yeah, and everything else is 0. Right? And because we have a lot of zeros in natural language processing, because we work with high-dimensional data sets, we typically use parse format. Right.
What does it mean, these ones? At the beginning, yes or no?
Yeah, so typically, positive. If you're building a spam filter, by convention, it would typically mean that something is spam. But I'm basically assuming that everything in life can be broken down to a binary classification problem. Of course it can, but most things in NLP can. So yeah, it's just the yes button. Okay. But that can mean a lot of things. I'm going to be talking about mostly topic classifications. So one is going to be just referring to one of the two topics that we're interested in. The data set that I'm going to be using, a very old school data set. It's 20 newsgroups. You've probably heard of it. It's a data set just consisting of newspaper articles. They're binned into 20 groups, so there are newspaper articles about IBM, motorcycles, the Middle East, atheism, and so on. But rather than thinking of this as a 20-way classification problem, what I'm going to be using it for is domain adaptation. The cool thing about the 20 newsgroups data set is that it has a hierarchical structure. So the 20 topics are organized in this hierarchy. So what we can do is that we can learn, for example, to distinguish sports from vehicles, but take baseball and cars as our training data and test it on hockey and motorcycles, for example, okay, which would be a domain adaptation problem. We can extract 280 different domain adaptation problems from the 20 newsgroups. So we have a lot of different data sets. And part of one of the take-home messages today is that when you do domain adaptation, you need to look at how sensitive your methods are to the amount of bias you're seeing in your data. So it's nice to have these data sets where you can take out 280 problems and organize or sort of order them with respect to how much bias you're seeing. Okay. Right, but that's what I'm going to be using. Then at the end, I'm going to return to more sexy topics like tagging and parsing. As I said, I'm going to focus on some very simple learning algorithms. Sometimes I'm going to be referring to more state-of-the-art learning algorithms. But essentially, I think that everything sort of boils down to these three methods. It's not 100% true, but I think an important... one of the important things that I like to say to my students, for example, is so in NLP, a lot of people I know in NLP, what they do when they work on a problem is that they take all the learning algorithms that they can think of and they try them out and they see what works best. I don't think that's a very interesting way of going about doing NLP research. The reason is that the fact that SVMs perform better than everything else in your specific data set doesn't say anything apart from just that SVMs work best on your data set. Unless you're just interested in exactly that test set, that's really uninteresting, because what happens if you vary things a bit? And you're working on the small finite sample. So I think one way to go about it is understanding the kind of assumptions that learning algorithms make and see how sensitive they are to those assumptions being violated, given that NLP data is typically very heterogeneous. So I'm just going to run through a couple of the assumptions made by a lot of learning algorithms, because I think they're important to keep in mind, and I'm going to refer to some of them. So these are at least the first two are the most basic assumptions in machine learning. The first one is the smoothness assumption. What that really means is just that if you have two data points, two vectors that are very, very similar, they tend to belong to the same class. So we're learning this function from these vectors to classes, from the x's to the y's, and we're just making this assumption that if things are similar, they are probably belonging to the same class. Not necessarily, but in general, right? That's important for learning. Think of your kids running around there on a farm or in the zoo. You go, that's a cow, and they see another animal, and it looks sort of like a cow. It's convenient if that's also a cow, right? Just, by and large, data points that look alike tend to belong to the same class. That's not always the case, but if it's not the case, like if your data violates the smoothness assumption, it indicates that you have the wrong feature representation. Okay? Or, the worst case is that the problem is not learnable. But it's important to check. And it's also the intuition behind most methods in feature selection. You want a feature representation that makes the smoothness assumption true as possible. Right. The second assumption is that data is identically and independently distributed. The fact that being independently distributed here means that, so in spam filtering, for example, if you get an email and it's spam, it doesn't change the probability of the next email being spam. When we get to structure prediction, we're going to be working with problems where the different data points are in fact dependent on each other. So if you're doing part of speech attacking and you say, gee, this is a noun, that's going to affect the probability of the next thing being a noun. But right now, we're just going to assume, by and large, that holds. It might not, but that's not what I'm going to be most interested in today. What I'm going to be really interested in is the other part of this assumption, namely that data is identically distributed. What that means is just that the test data was sampled more or less the same way as your training data. And that's typically not the case in NLP, right? When they constructed the Penn Tree Bank, they were gathering articles from the 89 or whatever edition of the Wall Street Journal, and that's not like the data that we actually want to process, typically. Two more assumptions that are at least important in general. One is the single cluster assumption. That's just that a class typically forms a coherent cluster. So in this case, you have a binary data set, and the classes seem to form different clusters. Down here, we have classes that are made out of two clusters. Now, that's important because some learning algorithms are actually assuming that classes form clusters, so the Perceptron, for example, cannot learn this kind of a problem. Neither can the naive Bayes. Nearest neighbor, however, is fine with that, as long as there's support for the different clusters. Okay. So it's important to keep in mind. Because or it's important when you evaluate the results you're getting using different learning algorithms. Low density separation is another common assumption, for example, in semi-supervised support vector machines. I'm briefly going to touch on that at some point. They're assuming that the best decision boundaries lie in low density regions. Right? And in some data sets, that's the case, in some it's not. So up here we have high density separation, so the best decision boundary here lies in a high density area. Whereas down here we have low density separation, and here we have something in between. Okay, these are common assumptions made in machine learning, and they're good to keep in mind. You can actually check whether this holds for your data. So you can actually go get numbers for these assumptions to see whether or not that's true for your data. I'm not going to talk too much about it, but I'm just going to mention that KL divergence is a common way of testing whether the data is identically distributed. And some of the methods that we're going to talk about later on will be using KL divergence. There are better ways of doing that in the literature, but KL divergence is the most common. You typically need special techniques for estimating KL divergence from finite samples, but I'm not going to talk about that today. All right, so here are the three learning algorithms that I'm going to introduce in this part of the talk. Just nearest neighbor. Are you all familiar with these methods? Right, okay. So the nearest neighbor is just about finding the data point that looks most like the data point that you're interested in, and you can use different distance measures. I'm going to run a small demo in a second. Naive Bayes computes the posterior probability of a class given a data point, and Perceptron is a discriminative classifier running through the different training data points to revise the model so that you get at least a reasonable fit to data. The reason that I'm going to talk about these three methods is because I think that there are sort of cornerstone methods representing like memory-based learning, probabilistic learning, and discriminative learning. And most methods, maybe apart from decision trees and rule-based learning algorithms, are kind of just extensions of one of these three methods or several of them. Right, here's how nearest neighbor works. For this toy example, you compute the distance from the test data point 0, 1, 1 to these three, and that's Manhattan distance-wise, or Hamming distance, it's 1, 3, 2, and you can also use Euclidean, except that in this case it doesn't really make sense. And you predict that the label of this data point is the label of the nearest neighbor, right? And you can go k nearest neighbor if you want to. In naive Bayes, you take, you use Bayes rule, so you take the prior probability and times the likelihood, and because of the independence assumption that all variables are independent given class, you can sort of factor that out, and it turns out that the join probability of spam and the test data point and non-spam and the test data point are both 0, and that's why you typically use smoothing. You're all familiar with this. That's why I'm going a bit fast. But using smoothing, you can, you get two different numbers there, and you predict that, this data point is spam because the join probability is slightly higher. And Perceptron is really just maintaining this model. So you start off with a random weight vector or initialize weights as 0, and you run through the different data points. So what you do is you take the dot product of the weight vector and the data point for every of your training data points, and you typically do several iterations over the data set. You start by your weight vector of, so it's 4 zeros because I'm encoding the bias term as neuron, if you like, or a variable. So you have this weight vector, and you augment this data point here with a -1, for example, and the dot product of that is going to be 0. And typically you say that, if the dot product is higher than 0, you predict positive, otherwise negative. So you're going to predict negative for this data point. And in this case, negative is going to be non-spam. So that's false, and you update the model. And the crucial thing here in the Perceptron is that you update by a fixed rate. So the update is going to be, for every weight here, it's going to be the original weight plus the true class minus the predicted class. So in this case, that's going to be 1. Times the learning rate, and in this case we've set that to 0.1. That's just the rate that you're updating the weight vector, and times the value of the variable, which is going to be 0. So that weight vector, or that weight in the weight vector, is still going to be 0 down here. However, when we have a value that's or a variable whose value is 1, you're going to see a change. So this weight vector becomes 0, 0.1, 0, minus 0.1. Right? Now it turns out that that's predicting the next data point to be spam. So we're updating again, and we end up with this weight vector, which gets this one right and predicts this one to be spam. So if we just do one iteration over the data, the Perceptron is also going to predict this data point to be spam. Right? Okay. I hope that's sort of enough to remind you what these 3 learning algorithms are doing. Typically in NLP, we do average perceptrons. So we store the different weight vectors that we're seeing, and we average them. So in this case, you would get something like this. Right. I'm going to get back to some of the intuitions as we go. Just a brief sort of first evaluation of these learning algorithms on 25 randomly extracted cross-domain data sets. Okay, so I'm just going to talk today about cross-domain data sets because I think that's another take-home message. We should always work on biased data because everything else is kind of an illusion. So what I've been doing here is I just randomly extract 25 data sets from the 20 newsgroups data set. That are cross-domain data sets, so like learning about sports and vehicles from cars and baseball, and testing on hockey and motorcycles. The numbers that you see here are just to tell you that, okay, gee, naive Bayes is slightly better than Perceptron, and nearest neighbor is a lot worse. That's probably not surprising to anyone in this room. What's interesting, however, is that if you look at how that correlates with the KL divergence of the 25 data sets that we're extracting, it turns out that Perceptron is less sensitive to KL divergence, right? And it's an interesting question. Why should Perceptron be less sensitive to domain differences? Okay, and I think that's the kind of questions we need to ask ourselves. I don't necessarily have a good answer. It might be that since rare features are less updated in the Perceptron model, but kick in with more in the naive Bayes model, that essentially when you go to a domain that's very different, the naive Bayes is going to be very biased by any potential, or by getting some of the rare features wrong. Whereas the Perceptron is really just going to care about very frequent features where you have more support. But these are the kind of questions that I think we should really be asking ourselves. This plot is just showing you that like these are 25 data sets, and I just drew lines here so it's easy to follow. What you see here is that, sometimes the Perceptron is a lot better than the naive Bayes, but generally naive Bayes is better. And these are the data sets where you see a lot of like big domain differences. Okay. For the rest of the talk, it's going to be important to extend these three learning algorithms so that they can accept weighted data. Weighted data here is just adding a weight to our data points. Our data points consist of this class label and the vector. I'm going to add a third thing into the tuple here, that's going to be a weight. What that weight is doing is not going to be terribly important right now, but the intuition here is that, for example, if we want to parse Facebook updates using Wall Street Journal data, down the road we want maybe to assign weights to the Wall Street Journal sentences because some sentences in Wall Street Journal look more like Facebook updates than others, or some look much less like Facebook updates than others. So maybe we want to downweight some of those sentences. So it's going to be important to work with weighted input, and that's also going to be important for my formulation of EM in a second. All right, so turns out this is relatively easy for all the three algorithms. So for naive Bayes, you basically just do a weighted map estimate. So when you compute the relative frequencies here, rather than letting every data point count by one, it's just counting by its weight. So you get almost the same joint probabilities, but they're so the prior probability, for example, of the spam class here is not 1/3, but 0.7 over 1.9, right? And that's essentially how it works out. In the nearest neighbor, the single nearest neighbor doesn't really, can't really deal with weights, but if you go k nearest neighbor so in k nearest neighbor, you find the k nearest neighbors and you let them vote on the class of something. And then it's really easy to work with weights because you're basically just doing weighted voting, right? So you find the three nearest neighbors and you let them vote by their weights, so to speak. Okay. In the Perceptron learning case, it's also very simple because we have this learning rate. Okay, so geometrically, in the Perceptron is about moving this linear decision boundary around in space, and you can find something you can't classify. You're moving a bit toward that data point. In the weighted case, we're just going to make the update dependent on the data point. So if you see something that you can't classify and it seems important or it has a high weight, we're going to move a lot. If it's not important, or it doesn't seem very important, we're just going to move a little, intuitively. Okay. Now, y'all know that these three learning algorithms are not, the kind of learning algorithms your advisor will tell you to use as your sort of first shot. But you can do weighted learning for things like passive-aggressive, Perceptron learning, Myra, and SVM2. I'm not going to run through the details. For SVM, it's basically about weighting the capacity constant. But I just want to say that you can do it. And I'm going to be presenting some results where we're using weighted Myra, and I think. Can't remember. But you can do it. All right, so that's supervised learning. Very short, fast crash course. Any questions at this point? Right. Okay, now supervised learning, the learning algorithms we've talked about so far, they assume that the data is smooth and that it's identically sampled randomly. The last thing is typically not the case in NLP. So we're interested in correcting the bias that we see in our training data. Semi-supervised learning can do that to some extent. Semi-supervised learning is about learning from a mixture of unlabeled and labeled data exploiting the marginal distribution of the unlabeled data. If that unlabeled data is sampled from the target domain, right? So you do self-training or something like that, and you take the unlabeled data from the domain you're really interested in. If you're adapting to that data, the unlabeled data, you're going to be implicitly adapting to the domain from which you pull that data. Okay? And it's actually what most people are doing when they do domain adaptation in the NLP literature. Like if you go to ACL Web and you look at papers doing domain adaptation, a lot of them are actually doing semi-supervised learning. I'm briefly going to run through these methods here. Self-training, co-training, and EM. Some of it is probably familiar to you. This is self-training. So self-training is this like simple thing. You take your parser, your classifier, and you classify a lot of unlabeled data, and you make that your new training data, and you retrain your model. That's essentially self-training. Now there are a lot of parameters here. So in some self-training setups, you only import pseudo-labeled data that you're really confident about. So you go to the unlabeled data, you try to classify it, and only if you're confident, say more than 90% sure about the class, you label that data point and make that your new training data. Of course, the problem with that is that you're typically confident about a specific type of data point. So in part-of-speech tagging, you might be really, really good at nouns, so you're going to import a lot of nouns or sentences with a lot of nouns. And then at some point, everything your training data is going to be nouns, and you're just going to be predicting nouns all the time. Well-known caveat in self-training. But yeah, that's self-training. There are variations. So one is I want to go to EM, and one step along the way is this slight variation of self-training. So the difference here. So here we just have this L variable, that's the labeled data set, and we're just continuously adding data to the pile of labeled data that we're training our model on, potentially doing several iterations over the unlabeled data. But here, we're putting it over in this L0, and what that means is just that every time, for every new iteration of self-training, we're just adding to the original data set. So we're not actually keeping the data that we labeled in the first round. So we can relabel the same unlabeled data points several times. And sometimes that's a good idea in self-training, but it's also important for getting this algorithm, which is essentially EM. It's just a very non-standard way of representing it. So EM is in the semi-supervised case. It's really just what's known as delible self-training. That is where you can relabel the same data points. But instead of just importing the unlabeled data points with your prediction, what you do is you take different copies of that data point. So if you're in the binary case, you take 2 copies. And if your classifier says that there's a 70% probability that this is a positive data point, you assign the weight 0.7 to the positive version of that data point, and the negative version you assign the weight 0.3. Okay. Otherwise, it's just delible self-training. And one nice way of, or one reason to look at it this way is that this is really easy to implement if you have a weighted classifier. It's really just self-training. Now, this is just a graph I wanted to show because it looks really good. This is doing several rounds of EM, and what you can see here is just that on this particular data set, the hockey motorcycles to baseball autos, self-training works out really well, or EM works out really well. So you're actually starting off with an accuracy of about 91% and end up with something like 96.5. For the 20 news groups is a really relatively easy data set, and this is using unlabeled data from the target domain. And self-training works out relatively well on 20 news groups. It typically doesn't because self-training is not a very robust method. And I'm going to talk more about it when we get back to parsing, where self-training typically doesn't work if you just do standalone self-training. That's why people have come up with other methods in semi-supervised learning. You probably know of co-training. It's basically just, in the original version, you split the feature set in 2 different sets, and you train a classifier, the same classifier, on the 2 splits, and you let them label all the unlabeled data points. Either they're both allowed to look at each other's predictions, or you just let one classifier label data points for the other. Which is like a split view co-training thing. Notice that given that the way we formulated EM just a second ago as basically just bringing in 2 copies in the binary case of the unlabeled data points with weights, it's easy to combine co-training and EM. And it's been done before by Nigam, and it's called Co-EM. It's a kind of algorithm that I would recommend if you want to do semi-supervised learning. It's kind of interesting to think about why this turns out to be a more robust algorithm. I'm going to get back to that question. Here's a little comparison, pulling just one unlabeled data point in each iteration. That's why the plot looks the way it does. This is a comparison of self-training and just random code training, where you split the features, but randomly ask one of the two classifiers. This is standard code training, doing slightly better, and this is just the soft self-training, just essentially EM, on 20 news groups, whatever that tells you. This is using naive Bayes as the... So notice that all these semi-supervised learning algorithms apply to all the learning algorithms that I've talked about and all the learning algorithms that you know of. EM requires weighted input and a confidence output to work, right? The others don't. Okay, another recently proposed and I guess to some extent widely used algorithm, semi-supervised learning algorithm in the NLP community is try-training. Now, try-training is really a very simple extension of code training, removing a parameter. So remember that back in code training, we had the same, just like in self-training, we have a selection, a criterion, and we have how long do you run for as a parameter. In try-training, the intuition is very simple. Sorry about the code. Don't worry about it. Look at me. So what try-training is really about is you take three classifiers. So in the original formulation by Lee and Su, what they do bootstrap sampling. So they basically do 3 different copies of the data set, and they train 3 classifiers on it. And what they do is that they say that, okay, if 2 classifiers agree on an unlabeled data point, we're going to feed that with the prediction to the third. And you do that in, all 3 ways, right? That's kind of like code training, except that the selection criterion here is the agreement of the 2 remaining classifiers. So you're removing that parameter from the model, so there's less parameter tuning. That actually turns out to be a relatively robust algorithm. Interestingly, you don't have to do bootstrap sampling to get your 3 classifiers. You can split the feature space, or the feature representation, feature set in 3 portions, or you can just use 3 different learning algorithms. Okay. I'm going to mention try-training a couple of times when we get back to parsing. Okay. Now here's a little sum up on semi-supervised learning. So semi-supervised learning may correct data bias, but what should be apparent by now is, since semi-supervised learning is really about labeling unlabeled data, this is obviously going to depend on the expected error on the target distribution. So if we wanted to use semi-supervised learning for domain adaptation, that's just going to work if the domains are not so far apart that our accuracy hurts too much from it. Right? Because if we do really, really bad on labeling our unlabeled data, retraining on that unlabeled data is going to hurt, right? Because we're retraining on data with the wrong labels. And that's just the simple take-home message of this part of the talk. So now, the lessons learned so far are that, we have labeled data, but it's scarce and biased. We know we have semi-supervised learning algorithms in our toolbox. I guess most of the algorithms that I've talked about so far are algorithms that you've heard of. And they can correct some bias. But only in some cases, and you can use things like KL divergence to actually go look at the data and see whether you think it's realistic or not that semi-supervised learning will actually work. Okay. Now what we're going to do is try to go beyond that. Okay. And you might ask yourself, like, how can you possibly do that? I like to think of this as sort of an air balloon kind of scenario. Because, one thing you can do if you want to adapt to a bias is look at the data that you can sample, or if you want to adapt to a particular distribution, you can look at the data that you can sample from that distribution. That's what we do in semi-supervised learning. If you want to go beyond that, what can you possibly do? Well, you can't really get more, right? You can't bring more to your air balloon. So the only thing that's left is dropping the things you have already, so to speak. And there are three logical possibilities. Like in machine learning, we have data points, we have parameters, and we have features. And that's all we have. Okay? So we can try to drop those three things. I'm primarily going to focus on dropping data points or down-weighting data points, as already hinted at. I'm also going to talk a bit about dropping features, or basically fitting the feature representation to the target domain. I'm not going to talk too much about parameters, but there's something to be said about that, too. I'm going to talk about importance weighting, which is a particular line of thought or strand of research in transfer learning. The intuition is just that, when you have source data, source labeled data, we can try to learn a weight function that says something about how important our data points are going to be for modeling the target domain. And the reason that's, this plot here is supposed to illustrate why that might be a good idea. So here we have two underlying classes. So we have the dark gray class and the light gray class. They both consist of two clusters. But it turns out that in our data set, which is the crosses and the circles here, or the bullet points, we've oversampled from the lower dark gray area. You probably can't see that, but there are not too many dots up here. There are 10 sampled from this and 100 sampled from this region. Whereas for the other class, we've oversampled the upper light gray area, but undersampled from the lower light gray area. Okay, so if you learn if you fit a decision boundary, so if you learn using SVM or whatever, you fit a decision boundary or linear decision boundary to this data set, you're going to get something like the stipulated line here, right? Which has an error of about 25% on the original or on the true distribution. Now, if our test data also has a sample bias where you oversample from this and this area, you're going to be even more erroneous on the test data, of course. Now, in that scenario where you have a sample bias in the test data, if we just weighted our data points by how much they look like the test data, we would put more weight on the data points up here in the upper dark gray area, and more weight on the data points down here in the lower light gray area, right? Because they look much more like the test data points if we sample the opposite way for the test data. And if, we have the perfect weighting, we would end up with a perfect decision boundary, right? Because we're correcting the sample bias by the weighting. And that's going to be the fundamental intuition here, that we can somehow use a weighting over the data to correct for the sample bias or the distribution bias in the labeled data that we have. Now, the problem, of course, is what weight function should we use? How should we weight the data? And you can show theoretically that what we really want as our weight of every data point, x here, is the probability of that data point in the target domain over the probability of that in the source domain. The only problem is that we can't compute these density functions, right? Unless we make a lot of really, really strong assumptions about how the variables interact. So in the literature, there are some proposals as to how to estimate these weighting functions. I'm just going to run you through a couple of them. One is using domain classification. The intuition here is really simple. You have your source data. So let's make this parsing. So you have the Penn tree bank. You have your Facebook updates. You want to parse. So in order to assign weights to the Penn tree bank sentences, what you do is you take the yields of all your trees. So you just have your sentences and you have your Facebook sentences, and you train a text classifier to discriminate between the two. And then you run that using cross-validation or something on the Penn tree bank sentences. And you take the classifier's confidence for every Penn tree bank sentence that it's really a Facebook update and use that as a weight, right? Because if your classifier is any good, that's going to be the same as the probability of that data point belonging to the target domain over the probability of that belonging to the source domain. Okay. Of course, you need a classifier that's good at predicting probabilities. So don't use naive Bayes, maybe use logistic regression, for example. Another way of, so this goes back to Bianca. This is an old idea. Bickel and Sheffer did that too. Another thing you can do is use a perplexity, actually the inverse of perplexity. So if you train a language model for the target domain and run that on your source data, you can use perplexity as sort of a rough estimate of how much a sentence looks like something that's seen in the target domain. You can, of course, also try to make assumptions about the variables, like independence assumptions. Then you can compute some density function-like functions, or you can just look at just a subset of the variables, for example. Kernel and mean matching, slightly more technical. Another relatively easy to understand thing is you can just look at sort of randomly sample weight functions and look at what they do to your KL divergence. So if you assume that small KL divergence is the same as the target data being relatively close to the source data, you can just try to explicitly minimize that by applying your weight function, randomly sampled, for example, and look at what that's doing to your KL divergence and just picking the weight function that gives you the smallest possible KL divergence. These are at least most of the proposals in the literature. Okay. Here's just a small evaluation in the context of 20 news groups. What you see here is just 4 different data sets that we extracted, applying it to naive Bayes and Perceptron. And you typically see quite good improvements but again, 20 news groups is a very well-behaved data set. Sometimes it hurts, and I'm going to get back to why that's the case. It's really about the weight function overfitting your data. And that has to do with the complexity of computing density functions. Importance weighting has been used. I think there's more numbers later on, but importance weighting has been used for part-of-speech stacking and dependency parsing with nice results previously. You can also apply to another classification problem, word sense distribution. Sorry about the table here. This is a crossword. Ask me if you're interested. Okay, as I said, there's this problem that the importance weighting or importance weight functions can overfit the data. It turns out there are different ways of trying to solve. There are different proposals in the literature as to how to solve that problem. There's some nice work by Karina Cordes, for example, where they talk about binning the weights in quantiles. So basically, you take all your weights, you rank them, you cut them up in equal sized portions, and for every bin, you take the average weight in that bin. And theoretically, that works if you know what number of bins you want to use. The problem is that if you don't have any labeled data from the target domain, which, by the way, I'm not assuming, I don't think I said that, but I think that's the realistic evaluation scenario in most NLP applications, then you don't know what the right number of bins is. And it turns out in practice you can't just use, at least in the experiments that we've been doing, you can't just say, let's go for 100 or 10 and expect that to work. And that's actually the nice open problem here. Other people like Zhang and Tsai have just done threshold. So basically you just take all the data points with weight higher than this, and you just include that, make that your training data set, and you throw everything else out. That's a very crude way of making importance weighting more robust, or avoiding overfitting, increasing the inductive bias, if you like. Right. There are more things to be said about that. It's an interesting problem. But now I'm just going to talk about something very different. So in domain adaptation, there's also been work on dropping features. So this was about dropping data points or down-weighting data points. You might also think that some of the features, for example, in document classification, some of the features you have in your model are going to be more relevant when you go to a target domain. So in topic classification, for example, some words are going to change meaning if you go to a new domain. Some are not just not going to be there, and so on. and some are just going to be without any predictive power. So here's a nice example. This is John Blitz's work motivating what's known as structural correspondence learning. This is sentiment analysis. So assume here that we're going from, we want to learn whether a review is positive or negative. We're going from reviews of technical equipment to reviews of tourist sites. So again, a domain adaptation problem. Learning positive and negative, but going from technical equipment to tourist sites. So like if you, in the training data, you see something like the cell phone is horrible. Like that's okay training data, because, you know, if a museum is horrible, that's also negative. But if you see something like the cell phone is handy, that's probably not going to be very applicable in the target domain, because, you know, who knows what a museum is handy means. So that's a feature that's just not going to be relevant. Okay, I'm going to return to that when we get to robust learning, this out of vocabulary related issue here. But worse off, some features might also change polarity. So a cell phone is small, that's good, but, you know, a museum is small, that's less good. So they have a nice theory that I just want to mention it because there's been a lot of fuss about this theory in the NLP community for a lot of good reasons. Structural correspondence learning works out as follows. So basically, you try to first limit your feature space to features that seem to have support in both domains, that are just frequent in both domains. You can do that, you know, because you don't need your labels to see that. Then, optionally, you also take just the features that seem to correlate with class in your source domain. But the real thing here is that then, in using target domain data, you train classifiers to predict the occurrence of the features that have support in both domains. So, horrible might be a good feature in sentiment analysis, so you train a text classifier-like model to predict the occurrence of the word horrible. And you can do that even if you only have unlabeled data in your target domain, right? And the intuition is that all the features that are predictive of that are going to be also predictive of whatever horrible is predictive of, right? So you can use the weights in that model, so to speak, as indicators of the polarity in the sentiment analysis case of those other features that you haven't seen in your original training data and the source data, but you're only seeing in the target data, right? Right. So they basically augment the data set with these features from the target data and retrain their model. Another approach to fitting the feature representation to a target domain is very related to what we just saw in importance weighting. There's a nice paper on just doing random subspaces and seeing what random subspaces minimize the KL divergence. Of course, you need some restrictions on your subspaces for that to work. Because otherwise you can just, you know, say, I'm going to make my only feature in a backwards model, for example. But apart from that, that's a very intuitive way of going about it. That's not learning anything about features not seen in the source data. It's just getting rid of all the irrelevant features. Right. Okay. So that was like a brief tour of transfer learning. The lessons now are that, so we have scarce bias data, we have semi-supervised learning that can fix some of our problems, but if the target domain is known, which is also an assumption made when you apply semi-supervised learning to these kind of problems, we can correct further bias using importance weighting, and it turns out that we can do that in more cases, so we don't need the expected error on the target distribution to be low, at least not theoretically. So this applies in more cases. But we've also noted that there's this problem of overfitting the weight function. And I'm going to try to bring that into parsing and tacking in a second. But I just want to consider I think, in a lot of ways, more interesting scenario where the target is not known. I know that for a lot of applications, or for a lot of scenarios like you work with the bioinformatics people scenario, the target domain is known, and then of course you should, pull as much data as you can to know what you're dealing with. But if you're designing NLP tools or online services and so on, you don't. And second, all the techniques that would work where you don't know the target domain should also work when you know the target domain. So I'm going to consider that scenario now. So this is the robust learning scenario, but I'm going to go a bit beyond that by assuming something about the source-target differences. And the main thing that I'm going to assume here today is just that what you see when you go to a new domain is more out-of-vocabulary items, right? So typically, within a domain, you have an out-of-vocabulary rate of something, 10%, whatever. But if you go out of domain, that's going to be more. Okay. Now, it's interesting to think, like, why is that a problem? It just means that there are some features that we don't have support for anymore. But why should that be a problem? Well, it's a problem because the optimal decision boundary in an n-dimensional space is not necessarily the optimal decision boundary in a limited space with fewer dimensions. A very, very simple example is the plot that I made here. So the support vector decision boundary here is the non-horizontal line here, this one. It's the best way of fitting to this data set. If you, at test time, throw away one dimension here, that could be turned into this decision boundary here, which obviously doesn't look too good. But if you knew that already, and you just learned your decision boundary from just that dimension, you would get something like this, which would be a lot better, right? Now, of course, that's assuming that you know exactly what kind of loss or what kind of missing features you're going to see, and we don't. But that's sort of the intuition. What we're going to do is we're going to try to essentially minimize the expected error across, or we're going to minimize the average expected error across the different possible losses that we can see. Okay? I'm going to get back to how that works. I just want to note that, of course, a lot of people have argued that this is one of the main reasons for performance drops when evaluating out of domain, and there's been a lot of work on that, spelling expansion, morphological expansion, and so on. And word clustering is very popular too, and that's all relevant. But all these different methods introduce noise, and they don't solve the problem 100%. So this is just complementary to that. It shouldn't introduce too much new noise, and you can just add it on as an independent module if you like. Right. So you might ask, so what do we already have in our toolbox that we can? Of course, we know that some learning algorithms are more global in the sense that they exploit a wider range of features. So, like decision trees are early discrimination algorithms. They look at just one feature, and if that's not there, you have a problem. Some of our learning algorithms, like nearest neighbor, for example, put a lot of weight on a lot of different features, which is generally a good thing. The problem with nearest neighbor is that it doesn't have a lot of inductive bias, so it's a very expressive formalism, and that's also going to hurt in the domain annotation case. For those of you who know anything about regularization, something like doing L-infinite regularization is something that's in at least the standard machine learning package that can solve some of this. What that's saying is essentially put a lot of weight on a lot of different features, whereas, for example, L1 regularization tends to give you some features with a lot of weight and a lot of features without. And that's probably going to be a bad idea if you're working with missing features. Note that we can use importance weighting because we don't know what target domain we're fitting to here. We can't use structural correspondence learning. We can't use KL divergence and random subspaces because we can't compute the KL divergence because we don't have any unlabeled data from the target domain. Okay, what we're going to do is inspired by old work in robust optimization. So robust optimization is really sort of, so typically you want to minimize expected error. In robust optimization, they're typically interested in the worst case of corruption. So assume that you're working on a problem and you have this evil enemy that's just going to corrupt either your data or your model or whatever. And robust optimization in general is just about minimizing expected error in the possible worst case. What we're going to do here is not exactly that. We're going to be more interested in minimizing the average case, though I think actually that considering minimizing worst case might work too. I just didn't do it. So we're going to be trying to minimize the sum of losses over possible corruptions, and a corruption here is just going from one domain to the other and the out of vocabulary effect that has. So we're going to try to gear our models to out of vocabulary effects, minimizing expected error on all the out of vocabulary effects that we can possibly think of. Okay. Now, one way of doing that is by throwing in just a vector that's going to cancel off features. So basically, you just multiply in a binary vector, for example, and a 0 is going to cancel a feature, 1 is going to keep it there. So you can think of standard supervised learning as just having this vector of all ones, and you're just interested in minimizing standard expected error. But what we're going to do is we're going to try to basically minimize the expected sum of error, if you like, over some set of cancellations of features. Okay. What we're going to do is we're going to randomly extract or randomly sample those vectors, okay, corresponding to different kind of OAV effects. Later, we're going to talk about feature weighting too, but essentially, what we're doing here is just trying to learn so that we get the best possible model for all scenarios where you throw away randomly 10% of your features, for example. Does that intuitively make sense to you? Okay, great. So one way of doing that that's kind of heuristic in a way is just taking your normal average Perceptron algorithm. So this is the average Perceptron algorithm. So you have your data set, and typically you just do this part. So for k iterations over your data, you're going to run through n different data points, and if you're not predicting the thing right, you're going to update your weight vector. Okay, this is a more generic, so you can put in the Myra update or the passive-aggressive update or whatever you want to do here. But this is just the average Perceptron. What we're going to do is that we're going to run sort of on top of that, or in an outer loop, are different runs of the average Perceptron algorithm. And for each R here, we're going to extract a random binary vector. And we're just going to, throw that in. Okay? So it's just doing this on different subsets. Okay? It's very simple. It takes, if R is 20, it's going to take 20 times longer, but at test time, it's going to be the same. Great. Note that in principle, you could extract your binary vectors at this level instead, or at this level instead. And it turns out that there's actually an old paper doing it at this level. So that would be corrupting every data point, but in a new way all the time. Okay. All right. This turns out to work relatively well too. Again, this is just 25 randomly extracted cross-domain data sets from the 20 news groups, and you see these error reductions of 9, 10-ish%. This is the number of rounds that we do, the value of R, so the number of random subspaces that we're considering. And what you see here is that you get better results if you include more random subspaces. Yeah.
When you had, for example, a lot of features, then I'm just thinking that for this to be effective, you would need a lot of the cancellations data.
Right. Yeah, okay, so one thing that I'm not saying here is that I'm canceling out random 10% of the features. That's just a heuristic. But of course, that's something you can, that's a parameter that you can set looking at your data. And it should probably be higher, just 10% here. The algorithm is relatively robust towards these things because, as long as you do, it seems as long as you do 50 or more rounds, like you're sort of covering the basics, so to speak. And it, at least on 20 newsgroups, but you should do this on much more, or many more data sets. It doesn't matter too much whether you're doing canceling off 10 or 15% of your features. Yeah, I think the empirical out of vocabulary rate here is, I can't remember, but that's something you can check. It's probably a bit higher than 10%, I would expect. Any other questions? Right. These are a bit hard to see, I guess, but they're basically just saying whether the error reduction. So back here, these are averages across 25 data sets, and these are just plotting the individual data sets. So you can see that in some cases, our technique hurts, but in most cases it doesn't. So everything that's below the red stipulated line is hurting performance. So the model is not perfect at all. It's just that it tends to be good. This is comparing our model against more advanced learning algorithms. And just the interesting note here is that the confidence-weighted learning, which is a recent learning algorithm, some of you might know it, is actually doing really good on cross-domain data sets, it seems. And I think it's an interesting question why that is so. Now, the algorithm that I've been showing you is very related to a lot of algorithms out there in the literature. There is something called random subspaces method. I think that comes with Weka or RapidMiner or any of these popular environments. It's old and it was invented in the context of decision trees. What they do is basically they take majority votes of an ensemble of decision trees learned in random subspaces. It's very similar to what we're doing here, except that we're formulating this explicit objective. It's also related to something that called feature backing and partition logistic regression. I'm not going to go into that because I don't have that much time left. I also want to mention that there's some work on that in the SVM literature. Dekel and Shamir were the ones who did the weighting per data point that I just referred to. And they also do L-infinite regularization. Some of these do consider, rather than sampling these binary vectors, you could in principle also sample real-valued vectors and basically just think of the domain effect as just a reweighting of your features, which would be more in the spirit of importance weighting rather than just blocking features. And it turns out that's actually a good idea, but it's really important what distribution you're sampling your real-valued vector is from. This is a bit tongue-in-cheek-ish, but try to follow me on this one. So here I'm using stochastic gradient with Hinch loss, stochastic gradient descent. That's kind of an SVM-like learning algorithm. What I'm comparing here is just the standard supervised learning algorithm. The B SGD here is using binary vectors, so what we just talked about. The Siphian here is drawing the real-valued weights by taking the inverse of a Siphian. So the intuition here is that from a Siphian distribution in one, like the source, for example, the target, which is also a Siphian, is going to look like a Siphian. Okay? That's the underlying intuition here. And it turns out to be consistently better than using binary vectors. These are the averages across these 4 data sets that I've referred to a couple of times. Interesting thing here, I've augmented the 20 newsgroups data set with Twitter data. Twitter tweets about the same 20 topics. And what we see here, there's a really, really small difference here between the robust and the non-robust on the domain annotation problem, but that's because you don't have a lot of bias for these 4 extracted data sets, which is why the accuracy here is really good. If you go Twitter, performance is slightly worse for the supervised system, but the improvement is a lot better. And if you do both newspaper to Twitter and topic domain annotation at the same time, you get even bigger improvements relative to the supervised system. This is over 25 randomly extracted data sets. right? I hope you get the difference. So I'm just extracting these Siphian real-valued or inverse Siphian vectors rather than binary vectors, and just multiplying them into the data set. All right. Okay, so far, what I've said is label data as scarce and biased. You can use semi-supervised learning in some cases. You can use importance weighting in some cases, but that relies on the assumption that you can actually pull unlabeled data from the target domain. If not, there are other things you can do going beyond robust learning a bit by assuming something very generic about what a source target domain difference is. And what we've been assuming here is that you see a lot of out-of-vocabulary effects. I don't think I have time to do the crazy idea here, but ask me questions about it. It's basically going a bit further beyond robust learning, actually looking at the individual data point and changing the model at test time. So ask me questions about that. There are some nice results in sentiment analysis. But what I want to say a couple of words about is how this applies to part-of-speech tagging and dependency parsing. So you're probably all familiar with this. There are essentially two different ways of doing structure prediction. One is consecutive classification, where you basically just take your last prediction, make that a feature for the next classification problem instance. So the transition-based parsers in dependency parsing, I guess you're all familiar with dependency parsing, they're doing that. Another way is using classification algorithms. So this is just using classifiers, really. You just do it in the specific order. The other way is using the classifiers as scoring algorithms, basically scoring the edges of a graph and then computing either a shortest path in the case of Viterbi-based part-of-speech, like the HMM scenario, or a minimum spanning tree, for example, in the MST parser. And these are roughly the two different ways of doing structure prediction. Yeah, as I said, the two things that I'm going to be interested in are part-of-speech tagging and dependency parsing. This is from Jennifer Foster's Twitter data set. It's one of my favorite analyses. Right. So just to step back for a moment and think, why are we doing this? Part-of-speech tagging and dependency parsing are really good cases for doing domain adaptation. Or bias correction, because these things are like treebanks are really expensive. Some have reported an annotation rate of 40 words per hour. If you want a decent-sized treebank, that means that it takes about 5 years to construct a treebank. You might argue with that. I have no experience in treebanking whatsoever. But if you take that as your number, and you think of all the possible use cases that we're interested in as NLP people, you can sort of say, take 5 years times the number of languages, which is something like 7,000, times the number of domains, which is probably infinite, times, some factor for language change, because, Wall Street Journal 89 is nothing like Wall Street Journal 2012, plus within population variance relating to dialects and, gender differences and whatnot. So that's going to be expensive, and that's why we're interested in doing this. And just to recap, we see these performance drops. They're prohibitive. We see them in dependency parsing, constituent-based parsing, all over the place. And it turns out that, for English, they're bad, but for other languages, they're even worse. Probably not for Czech, I don't know. But if you have a smaller tree bank and it's newspaper articles, you're going to be more vulnerable, even more vulnerable to domain change, right? Because you have less support. With a small size tree bank. So in Danish, if you go spoken language, you're lost. Okay, so what's in our toolbox now, given what we've talked about? So one thing that I haven't talked about is using clusters as features. That's probably the most widely used semi-supervised learning technique in parsing. So the idea here is that you take a clustering algorithm, you do word clustering. So you do Brown clustering, which is hierarchical clustering combined with a bigram language model. And so you get these clusters of words that tend to, have equal distributions, or have the same kind of distributions, and you just augment your tree banks with them. Because that means that you can generalize to unseen words, maybe to some extent. We have our semi-supervised wrapper methods, importance weighting, feature-based transfer learning, robust learning. I'm going to try to comment a bit on all of them. So clusters as features dates back to Terry Koo. Maybe there's been earlier work, but I'm not familiar with it. 2008 paper. And what he was doing is taking these Brown clusters, so these bit vectors here are basically just names of clusters. And he would just augment the tree bank with these clusters, so we had not just words and parts of speech, but also these distributional clusters. And he would actually use them at different granularities, because in hierarchical clustering you get this hierarchy of clusters, so you can cut it at different levels. This turns out to work really well. And I'm going to talk a bit about the parsing the web shared task, which is a recent shared task on parsing Web 2.0 data. And pretty much everybody used this technique in that shared task. So it looks as something that's become standard. It's also been used in part-of-speech tagging, name entity recognition, SMT, and semantic parsing. You can use other kind of, so this structure here is actually a dependency structure with the clusters. They're just really hard to see because it's a 50-dimensional cluster in a neural network. But you know, there are different clustering algorithms, but most people use Brown clustering, I guess. Self-training, which is one of our semi-supervised wrapper methods, is often reported not to work if you just take a parser, parse some unlabeled data, and retrain. The positive results are typically on very small amounts of labeled data. But there are these tweaks that have made self-training work. One is David McCloskey's work, where he basically self-trained a parser, but then applied a re-ranker and self-trained the parser using the new sentences that he got from the re-ranker. So there was this intermediate step giving a bit of diversity, which is sort of like something that looks a little like code training. Because you really have two different systems, and one is feeding the other. And I think that diversity is important to get something like self-training to work. The Kyle 2007 shared task on domain adaptation was probably the point where people started to talk about domain adaptation and parsing. It was won by Sagi and Suri. They used a very simple form of code training. We've done some work with tri-training, but that has not been on bias data. That's been on in-domain data. But there we, I think I have a results table in a second. Rue et al., so that's also Jennifer, that's the DCU Paris group that participated in the parsing the web shared task this year. They won that shared task, and they used an ensemble of self-trained parsers, basically trained on different samples, and combined them in a product of expert, which is product of experts. It's kind of interesting to try to see the sort of the overall picture here, because while self-training doesn't work, self-training with a re-ranker seems to work, tri-training seems to work, and ensembles of self-trained parsers seem to work. So it seems that it's, in a way it's not very surprising, because one of the things you know from machine learning is that ensembles give you more robust classifiers. And all these are in some way constructing an ensemble with some parsers learning from other parsers. Structural correspondence learning has so far, as far as I know, been unsuccessful in the context of parsing. There are some good results in part-of-speech tagging, though, so I'm not going to talk too much about that. Here's a results table from our 2010 paper where we try to use a lot of semi-supervised learning techniques, but this is, again, on in-domain data. And this is just to say that most of these standard learning algorithms are typically not very robust. And one of the things we argue in that paper is that what we call generalized tri-training, which is not the original bootstrap sample-based version of tri-training, but one where you have different learning algorithms to create a more diverse sample, is one robust semi-supervised dependency parsing technique. But really, robustness is the issue here. This is going to be extremely hard to see for you guys. It's just a results table for the parsing the web shared task. And the only thing, well, there are two things to note. I'll tell you what it says up here. DCU and Paris won the shared task. Harbin was in, Stanford, we were in, IMS, Tokyo, UMass, UPenn. I think the most important thing in this table is that the part-of-speech tag, but you've seen that already, part-of-speech tagging accuracy is really, really low on this Web 2.0 data. And I think that's an extremely important take-home message. part-of-speech tagging is definitely not a solved a problem. But what I wanted to say here is just, again, re-emphasize that in NLP, most people, when they try to solve domain adaptation problems, like which was the explicit objective of this shared task, do semi-supervised learning. They typically do self-training. Some do tri-training, like the Harbin Institute of Technology. We tried to do importance weighting, but we were the only people in the shared task trying to do transfer learning. And I think there is a potential here that's not being exploited a lot. What we saw was that we also saw this problem in importance weighting, that the weight functions didn't seem very robust. So what we ended up doing, which is kind of related to what you see in semi-supervised or applications of semi-supervised learning algorithms to domain adaptation, was that combining a lot of different weight functions gave us a much more robust system. So basically, we would train parsers with different weight functions, and we would combine all of them. So we would have a parser which was trained on weighted data where the weights were perplexity scores, one where it was classification-based scores, and so on. These are the results. I'm not going to go too much into them, but what you see is that we got some nice improvements over the non-weighted case, both for the development data and for the test data. An interesting thing is that it's not just about combining parsers, because if you do standard ensemble methods like backing, you get some improvements, but not as much as you do with importance weighting. So importance weighting is playing a role here. But what you also see is that the individual weight function, so this is using single features to weigh the data. This is perplexity. This here is using a topic model, so like the unsupervised analog of using a classifier. Give you nice improvements, but what is best varies a lot across the different domains. So again, robustness seems to be the problem also in transfer learning or importance weighting. Just a slide saying that a lot of people have used importance weighting for other things, including cross-language dependency parsing, which is something that I'm super interested in. We're going to talk more about that maybe tomorrow. Yeah. I haven't done any experiments yet on using the robust or beyond robust algorithms I've talked about in the context of parsing, but I've been applying them to part-of-speech tagging recently with a very consistent improvements. That definitely seems to be a good idea. This is on the English web treebanks, so the same data that's been used in the parsing of the web share task. So the target domains here, just like in the previous slide, are Yahoo Answers, BBC Newsgroups, reviews, web blocks. Should have been emails in there. And you see these nice improvements of like about a percentage point or so. This is on the Penn treebank tag set, by the way, not the Google's universal part-of-speech tag set. This is the Danish treebank. It comes in 4 different sections: newspaper, law, literature, magazines. And this is training on newspapers, but testing on law, literature, and magazine. And again, you see these improvements. Here we have the binomial robust algorithm, and here we have the Zipfian. And this is with 25 subspaces, this is with 50, this is with 100. And the experiments on the English web treebank are still running on the server back home in Copenhagen for the 50 and the 100 subspaces, because it does take a while. Especially because the structure Perceptron, which is the Michael Collins model, is implemented in Python with not a lot of optimization there. All right, so this is my last slide. Sorry for going a bit over time. I guess these are the take-home messages. So I've talked about all this already. This was like the machine learning part of the talk. I guess what I want to say is that using semi-supervised learning algorithms, which is what a lot of people are doing, dealing with domain adaptation in NLP, is a good idea when domain differences are relatively small. So when KL divergence, for example, is relatively small. Importance weighting seems promising, but there is some work to be done on finding robust weight functions. And robust learning algorithms can learn to significant, or can lead to significant improvements even when the target is unknown. And I think, in general, what we should do now, I think sort of the time is right for doing large-scale evaluations of a lot of the techniques that I've been talking about, and trying to see whether we can combine a lot of these things. And I think the last take-home message would be that, and something that I'm actually not doing in the last slides here, I think what we really should do, rather than just to work on or just report like average results over 25 cross-domain data sets, is to look at how sensitive our methods are to domain differences. So like early on in the talk, I had this slide where I looked at the correlation between KL divergence and performance, because I think that's really what's important if we want to know how good our methods are when you're applying them to some problem, as a black box, as a user. Also, one of the things that you might see as a potential end product here is like a way of doing model selection based on the actual data that your parser comes shipped with this method that's just going to compute the KL divergence to the data that the user is using your parser for, and selecting the appropriate model or the appropriate technique based on that. And I think that's the kind of work we really should be doing now. Yeah, I think that's it. Thanks.
Thank you so much for the talk. It was so interesting. Let me warm up the discussion with a really silly question. You said that you perceive the three classifiers, NB and Perceptron, as the cornerstone. So could you please classify some more classifiers into these three classes?
Yeah, right. So like in NLP, like I guess, like if a student walks up to me and says, I have this problem, I just want to use the learning algorithms off the shelf, what should I use? I would say average Perceptron, Myra, support vector machines, and they would all, to me, be like off the standard Perceptron. Or I would say go graph-based, especially if they're dealing with semi-supervised problems. And they would be like nearest neighbor methods, basically. And of course, Bayesian networks would be, like if you get Naive Bayes, you're going to get Bayesian networks at some point. So yeah, and to me, that's pretty much machine learning, I guess.
So questions, please.
Okay, also a silly question, just maybe also terminology. So in domain adaptation, the task is that we have source domain and target domain, and we know what the target domain is, so we have at least some unlabeled data for the target domain.
Right.
And we can have also maybe a bit of label data from the target domain, so then it's...
Yeah, I'm actually not assuming that, and in general, I don't think that, like, for most applications, I don't think that's realistic. But in the NLP literature, a lot of people assume that, yeah.
Okay. Then there is a task you talk about where you have several domains, but not the target domains.
I'm actually not talking about multi-source domain scenarios. For some problems, I mean, you do have data sets from different domains, like sentiment analysis, for example. And it makes a lot of sense. So there's been nice work in parsing too by David McCloskey on basically parsing previously unseen domains, assuming that they are a mixture of domains that you know already. And that's super nice work, and definitely related to sort of the intuition here. What I'm saying is that I'm interested in two different scenarios. One where you have a source domain where you have labeled data, one where you have and target data, but only unlabeled data, and one where you have source data that's labeled, and then you're going to get some test data, but you don't know where it's coming from. So that can be sampled from any target domain. You just don't know what that domain is going to be in advance.
Well, I can imagine several approaches where you have like the 20 newsgroup domains, and the test or the target domain is something completely different, but still you can say that a robust learning algorithm must perform well on all of those 20 domains, and then you can hope that it will perform good also on the target domain. And then there is another task where where you have, let's say, just one training domain, and you know that the target domain will be completely different, and no training data. I don't know if there is a name for this, and if any of the approaches mentioned could work also for this. Let's say that you have only economics parsing training data, and how to recognize which features are robust enough. Let's say it seems that a feature that every sentence has mentioned $1 or I don't know another currency seems a robust feature. Is almost in every sentence in your training data. So
the problems that I'm considering here all just have one source domain. So is that the scenario you're talking about?
Yes, my question is, we have just one training domain and no other data, even unlabeled.
Right. That's the beyond robust learning part of this talk is assuming just that. And what the intuition here is that, okay, so we don't know anything about the target domain. What can we do? And what I'm saying is, well, one thing that we can do is we can try to come up with a class of likely distributions, like just potentially infinite class of distributions that we can envisage, and we can try to minimize the expected error across all of them, either worrying about the worst case or about the average case. And that's what I'm assuming here.
But if each sentence is talking about money, then you still probably would consider this as a good feature, or
well, so actually there's a typo there.
it's a silly question. Sorry, I don't know how to solve this.
Right.
I just wanted to.
So, in the algorithms that I'm looking at here, I'm randomly removing features. So the dollar feature can be removed, just as well as any other feature. And one possible extension of what I've been talking about here would be to, put maybe weights on features, say how likely is it that this feature is going to be out of the question when we get to a target domain. Because some features are definitely much more likely to disappear, like specific terms, for example, or domain-specific terms. But that's not something that I'm talking about here. One of the things that I didn't talk about today is how to think about different types of biases. One way so there are different kinds of biases in literature. There are sample biases. So I had this really nice slide. I should have. There are sample biases. So one way to think of that is you're learning to parse Wall Street Journal, but for some reason, when people did the annotation of the Wall Street Journal data in the Penn Tree Bank, they threw out all sentences with more than 50 words. Okay. I mean, they didn't, but let's assume they did. That would be a sample bias. So they sampled the data from a particular distribution in an unfair way, right? Because they were throwing out some data. And if you see that data in your test data, then you have the sample bias, right? You can also talk about what's sometimes called distribution biases. A distribution bias is, for example, going from Wall Street Journal to Facebook, right? There are probably, you might think of that as sample biases too, like if the underlying distribution is English, but you can also think of as just slightly different distributions, but with their own sort of coherent whatever. And the third kind of bias would be a problem bias, where there's actually something about the functional relation being different, so going from English to Arabic, like cross-language dependency parsing, or from syntactic parsing to semantic parsing. And I like to think of that whole thing as a continuum. And one way to carve it up a bit is, so there are basically three different kinds of biases that you can think of. In some cases, you just have a bias in the marginal distribution of data. So in domain adaptation, that's typically the case, right? In a sample, right? Okay. In a sample bias, by definition, you can only see either a bias in the marginal distribution or a bias in the distribution of classes, which is sometimes called a class imbalance problem. Because the underlying functional relation, if that's consistent in the underlying distribution, then how you sample your data is not going to affect this thing, right? But your ability to estimate it in a classifier is going to be affected well, at least for a lot of learning algorithms. If you see a bias here, it's probably a problem bias. But I think it's important to think about these things. And I think for most of the problems that I'm interested in, this is the kind of bias you see. Like, one way to think of it is, if you want to parse Facebook updates and you only have Wall Street Journal, what you're going to see is different sentences. You might see a different distribution of relative clauses or subjects or the kind of things that you're predicting. It's probably going to be the case, at least for this example. But I wouldn't expect that, given a good feature representation, that you would have real ambiguity, so you would have one syntactic analysis for the same sentence just because it's a Facebook update, but another if it was a Wall Street Journal sentence. At least I would think that the bias here would be extremely small. So this is one way of carving it up. In word sense distribution, you typically see, so there's been a lot of papers on class imbalance problems in word sense distribution because, if you have Wall Street Journal annotated word sense distribution data, you're going to see bang in the financial reading a lot, but if you go to Facebook, you're going to see the Riverside reading much more frequently. Of course, there you're also going to see a bias in marginal distribution. So this is one way of thinking of it, and all that I've been talking about today is trying to solve this problem. Okay. The importance weighting with perplexity, for example, that's solving this problem. I haven't been talking about these.
Let me thank you again.